Nice to meet you. My name is SeonWoo. Have you ever heard about how can material science contribute to the quantum world? In the past, scientists might like Carolus Goodyear developed new materials by accidental chemical reactions. But now, as the understanding degree of material science increases, the demand of exact measurement of material components and structures arise. As a result, material science had to study about new principles in quantum world that scientists have developed many devices using the principles of quantum world. Therefore, today I will introduce about quantum cascade lasers, which is one of the examples of the new technologies and which is the output of material scientists' contribution to the quantum world. First, to explain quantum cascade lasers, QCL, and each operation principle briefly. QCL are the semiconductor lasers that emit in mid to far infrared portion of electromagnetic spectrum. The existing semiconductors use bulk materials, which means relatively large material as layer, so electron occupy to one continuous valence band and emit laser photon through hole and electron combination. However, QCL uses superlattice, which means periodic series of thin layers with varied material composition for bandgap tuning, and when the quantum well are thin enough, their energy level blurred out and it makes varying electric potential and many subbands which electron can be occupied across the length of device. Then, once electron undergoes inter-subband transition in quantum well structure by applied external voltage, and once emits later in one period of superlattice in unipolar QCL, it can tunnel into next period, so it can make many photons by just one electron. And as a result, it makes high output powers than other semiconductor lasers. Furthermore, throughout superlattice in QCL, varied electric potential makes varying probability of electrons along to the position in device, and the thickness of each layer affects directly to the wave function of the subband. Thus, thickness of layer contributes to the energy level of subband more than the composition of the material in layer. Then we can reach to the laser energy area where we cannot approach through material change. This is useful to detect specific gases, and we can tailor emitting wavelengths simply by changing the thickness of the layer. Moreover, laser occurs from stimulated emission, which means incident photon makes excited electron transit to the ground state, and for stimulated emission, excited electron should be supplied more than electron with spontaneous emission. Then excited electron density becomes higher than the ground state density, which called population inversion. For QCL, which the assumption of formation of wave functions is the faster process than scattering, QCL system with population inversion and superlattice can be modeled by three-level system with rate equation modeling like this picture. Then we can apply time-independent solutions to Schrodinger equation. I will not explain this more because it is just one of the assumptions for making QCL. Then, second, I will show about Schrodinger equation solving process in QCL. If we assume QCL in framework of Band-Daniel-Duke model, which only considers the conduction band where the lasing transition and carrier transport occur, and if we assume the potential growth direction is z direction, the Schrodinger equation is like this. Here, M2 refers in plane effective mass, which is perpendicular to the growth direction and which is affected by material composition, lattice temperature, or doping level. And M star is effective mass in growth direction. Then, by normalization of wave function, we can get solution about wave function k, including in plane electron motion with wave vector k. By applying decoupling, we can ignore z dependence of M2, and by neglecting in-plane electron motion, we can yield one, one-dimensional Schrodinger equation in z direction. After this stage, if we consider boundary conditions, non-parabolicity, then we can get numerical solution for this equation, and as appendix by assumption of electron-electron interaction can be considered by self-consistency with low energy. we can apply Poisson equation for the solution of Schrodinger Poisson system model. Then finally, to show the usage of QCL and its application, nowadays QCL benefits its relatively low electrical power requirement and the size of device. QCL are used in gas sensing and measurement of gas species and concentrations. Thus, it can be used in not only industrial area but medical or security area with detection of specific chemical compounds. However, as today's QCL have limitation for general commercialization such as difficult manufacturing process, high cost for small size QCL, and sensitive to temperature change. Thus, more QCL application needs to be created and developed than it can be expected to QCL will become more available and affordable. To sum up, I talked about quantum cascade lasers and one of the technologies from quantum world and looked briefly into the operating principle and usage and applications. As we can see in this presentation, development of material science produced such a tremendous technology available. Thus, QCL can be one of the answer of how can material science contribute to the quantum world. Then like this case, coming material science progress is depending upon the exact analysis of material components and structures from the wide understanding about quantum world. Thank you for listening, and this is the list of the reference I used to make this presentation.